a multi-unit building, a single grounding electrode conductor connected to the uffer from the meter or main service equipment is sufficient for the entire building. Running separate grounding electrode conductors from each unit's load center to the uffer is unnecessary and can create potential safety hazards. The primary purpose of the grounding electrode conductor is to establish a low impedance path to ground for fault currents, ensuring the proper operation of overcurrent protective devices like circuit breakers and fuses. A single, properly sized grounding electrode conductor connected to the uffer from the main service provides an adequate path for all units within the building. Installing multiple grounding electrode conductors to the uffer doesn't enhance safety and can introduce complications. Firstly, it can create a ground loop. A ground loop occurs when multiple grounding paths exist, potentially causing current to flow through the building's structure. This circulating current can create a shock hazard and interfere with sensitive electronic equipment. Secondly, the National Electrical Code, or NEC, typically requires a single grounding electrode conductor to the uffer. Installing multiple conductors might not comply with code requirements and could lead to inspection failures. Flexible metal conduit, or FMC, used to feed each unit already includes an equipment grounding conductor, or EG. The EGC provides a low impedance path for fault currents back to the main service equipment, ensuring that overcurrent protective devices trip quickly and safely. The equipment grounding conductor within the flexible metal conduit serves to ground the metallic enclosures of the electrical system, providing a safe path for fault currents back to the source. The grounding electrode conductor, on the other hand, connects the electrical system to the earth, providing a reference point for voltage and helping to stabilize the system's potential. The combination of the equipment grounding conductor and the grounding electrode conductor ensures a comprehensive grounding system. Consider the scenario of a fault occurring within one of the units. The fault current would flow through the equipment grounding conductor in the flexible metal conduit back to the main service equipment. This would cause the overcurrent protective device, such as a circuit breaker, to trip, cutting off power to the unit and preventing a shock hazard. The grounding electrode conductor connected to the uffer provides a path for any residual fault current to dissipate into the earth. Let's delve deeper into the function of the uffer as a grounding electrode. Uffer is a concrete encased electrode, typically consisting of at least 20 feet of bare copper conductor encased within concrete. It provides a large surface area in contact with the earth, resulting in a low impedance grounding path. The NEC recognizes the uffer as an effective grounding electrode, and it is commonly used in new construction. When installing a grounding electrode conductor to the uffer, it's crucial to use the correct size conductor, as specified by the NEC. The size of the grounding electrode conductor is typically based on the size of the service entrance conductors. The connection between the grounding electrode conductor and the uffer must be made using approved methods such as exothermic welding or listed connectors. These methods ensure a reliable and low impedance connection. In summary, for a 4-unit apartment building, a single grounding electrode conductor connected to the uffer from the meter or main service equipment is sufficient. The electrician's installation of separate grounding electrode conductors from each unit's load center to the uffer was an overkill and potentially created a safety hazard. The equipment grounding conductors within the flexible metal conduit provide adequate grounding for each unit, and the single grounding electrode conductor connected to the uffer provides a path to ground for the entire building. It's essential to consult the NEC and local electrical codes to ensure compliance with grounding requirements. Improper grounding can lead to electrical shock hazards, equipment damage, and system malfunctions. Always prioritize safety and follow best practices when installing and maintaining electrical grounding systems. Also consider the material used for the grounding electrode conductor, which is typically copper. Copper provides excellent conductivity and corrosion resistance, making it a reliable choice for grounding applications. The grounding electrode conductor must be protected from physical damage. This may involve running the conductor through conduit or using other protective measures. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Check for loose connections, corrosion, and damage to the grounding electrode conductor. Correct any issues promptly to maintain a safe and reliable electrical system. The NEC provides detailed requirements for grounding and bonding, including conductor sizing, installation methods, and inspection procedures. Familiarize yourself with these requirements to ensure compliance and safety. Grounding and bonding are critical aspects of electrical safety. They protect people from electric shock, prevent equipment damage, and ensure the proper operation of electrical systems. Always follow best practices and consult with qualified electricians when working with electrical systems. Remember, electrical work can be dangerous. If you are not qualified, do not attempt to perform electrical work yourself. Hire a licensed electrician to ensure that the work is done safely and correctly. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Refer to NEC Table 250.66 for the appropriate conductor size. The grounding electrode conductor must be connected to the grounding electrode system, which includes the uffer, as well as any other available electrodes, such as metal water pipes or ground rods. The grounding electrode system provides a comprehensive grounding path for the electrical system. The connection between the grounding electrode conductor and the grounded electrode must be accessible for inspection and testing. This allows for verification of the grounding system's effectiveness. Regular testing of the grounding system can help identify potential problems before they become safety hazards. Grounding impedance testers can be used to measure the resistance of the grounding system. A low resistance indicates a good grounding path. A high resistance indicates a potential problem that needs to be addressed. The grounding electrode conductor must be installed in a manner that protects it from physical damage. This may involve running the conductor through conduit or using other protective measures. The grounding electrode conductor must be continuous and without splices. Splices can increase the resistance of the grounding path and reduce its effectiveness. The grounding electrode conductor must be securely fastened to the grounding electrode. This ensures a reliable and low impedance connection. The grounding electrode conductor must be identified with a green or green with yellow stripe insulation. This makes it easy to identify the grounding conductor and prevents accidental connections to other conductors. Grounding is a critical aspect of electrical safety. It protects people from electric shock, prevents equipment damage, and ensures the proper operation of electrical systems. Always follow best practices and consult with qualified electricians when working with electrical systems. If you are unsure about any aspect of grounding, consult with a licensed electrician. They can provide guidance and ensure that the grounding system is installed correctly. Improper grounding can have serious consequences. It can lead to electric shock, equipment damage, and even fire. Always take grounding seriously and follow best practices to ensure a safe and reliable electrical system. The grounding system is an integral part of the overall electrical system. It works in conjunction with other safety features, such as overcurrent protective devices, to protect people and equipment from electrical hazards. Understanding the principles of grounding is essential for anyone working with electrical systems. It is important to have a thorough understanding of the NEC requirements for grounding and bonding. The NEC is a comprehensive set of standards for electrical safety. Following the NEC requirements helps to ensure a safe and reliable electrical system. Grounding is not a one-size-fits-all solution. The specific grounding requirements for a building will depend on a number of factors, including the size of the building, the type of electrical system, and the local soil conditions. It is important to consult with a qualified electrician to determine the appropriate grounding system for a particular building. The grounding system should be inspected regularly to ensure that it is in good working order. Any problems with the grounding system should be corrected immediately. A properly installed and maintained grounding system is essential for electrical safety. It protects people from electric shock, prevents equipment damage, and ensures the proper operation of electrical systems. Grounding is a complex topic. There are many different types of grounding systems and many different ways to install them. It is important to have a thorough understanding of the principles of grounding before attempting to install or modify a grounding system. If you are unsure about any aspect of grounding, consult with a licensed electrician. They can provide guidance and ensure that the grounding system is installed correctly. Remember that electrical work can be dangerous and should only be performed by qualified individuals. The National Electrical Code, or NEC, Section 250 covers grounding and bonding requirements in detail. Familiarizing yourself with this section is crucial for anyone involved in electrical installations. It specifies the types of grounding electrodes permitted, the sizing of grounding electrode conductors, and the methods for connecting to grounding electrodes. NEC 250.50 discusses grounding electrode systems and the requirement for all available electrodes to be bonded together to form a single grounding electrode system. This includes metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The purpose of bonding all available electrodes together is to create a low impedance path to ground and minimize voltage differences between different parts of the grounding system. NEC 250.52 covers the types of grounding electrodes that are permitted, including concrete encased electrodes, often referred to as uffers. A concrete encased electrode must consist of at least 20 feet of bare copper conductor that is at least 0.5 inches in diameter and encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. NEC 250.66 provides guidelines for sizing the grounding electrode conductor. The size of the grounding electrode conductor is based on the size of the service entrance conductors. A table in this section provides the minimum size of the grounding electrode conductor for various service entrance conductor sizes. NEC 250.68 covers the methods for connecting to grounding electrodes. The connection must be made using approved methods such as exothermic welding or listed connectors. The connection must be accessible for inspection and testing. NEC 250.70 specifies the requirements for the grounding electrode conductor connection to electrodes. The connection must be made in a manner that ensures a permanent and effective ground path. Approved connectors and methods must be used to prevent corrosion and maintain a low impedance connection. NEC 250.104 covers bonding of metal water piping systems and other metal piping systems. These systems must be bonded to the grounding electrode system to minimize voltage differences and prevent shock hazards. The bonding jumper must be sized according to NEC Table 250.102. NEC 250.130 addresses equipment grounding conductor connections. It specifies the methods for connecting equipment grounding conductors to the grounding electrode system. The equipment grounding conductor provides a low impedance path for fault currents back to the source, ensuring that overcurrent protective devices trip quickly and safely. It is important to understand the difference between grounding and bonding. Grounding connects the electrical system to the earth, providing a reference point for voltage and helping to stabilize the system's potential. Bonding connects different metallic parts of the electrical system together, creating a low impedance path for fault currents. Both grounding and bonding are essential for electrical safety. When inspecting an electrical installation, it is important to verify that the grounding and bonding systems are installed correctly and that they meet the requirements of the NEC. Look for proper conductor sizing, secure connections, and proper identification of grounding conductors. If you find any problems, bring them to the attention of a qualified electrician. The grounding system is a critical component of the electrical system. It protects people from electric shock, prevents equipment damage, and ensures the proper operation of electrical systems. Always follow best practices and consult with qualified electricians when working with electrical systems. By adhering to the NEC and best practices, you can ensure a safe and reliable electrical installation. This includes ensuring the correct sizing of the grounding electrode conductor based on the service entrance conductors as outlined in NEC Table 250.66 and verifying that all connections to the grounding electrode are made using approved methods that maintain a low impedance path. Furthermore, regular inspection and testing of the grounding system are paramount to identify and rectify any potential issues, thus upholding the safety and reliability of the electrical system.